Listen, we need to shatter a massive illusion right out of the gate. You absolutely do not scale systems by just throwing more code and cloud resources at them. If you're a developer or an engineering leader watching your cloud costs spiral out of control while your app's performance barely moves, well, this explainer is exactly what you need. We're going to dive into what truly separates a junior contributor from a battle-hardened senior backend engineer. And honestly, it's probably the exact opposite of what you've been taught.
There's this core truth in our industry known as the deletion paradox. This is the hard truth that separates the seasoned architects from the eager beginners. You probably think senior developers got to where they are by writing elegant algorithms and architecting these massive, beautiful systems from scratch, right? Wrong. They got there by becoming ruthless deleters of code and complexity. They know that building features is just half the job. The other half is keeping the system lean enough to actually survive in production.
Picture this. A junior developer joins a team. They're super eager. They implement new APIs, add validation layers, and might pump out 50,000 lines of code in their first year. If you look at their code graph, it shows these massive mountain peaks of added features. Now, a senior engineer joins that exact same team. In their first month, they delete 15,000 lines of code. Their graph looks like a valley. Why? Because they're hunting down technical debt, ripping out redundant microservices, and lowering the cognitive load for everyone else. Every single line of code is a liability. It creates dependencies, demands maintenance, and, crucially, it literally costs money to compute.
All right, Section 1, the senior engineer mindset, moving from creation to systemic deletion.
Before you even think about re-architecting your app or tossing more compute at a problem, remember this absolute golden rule. Visibility must precede modernization. You cannot safely accelerate a system you do not understand. Period. Remember, latency is a system's property. It's the sum of all your architectural choices across the entire stack, not just one isolated, slow database query. Also, tribal knowledge? That's a single point of failure in any organization. If your infrastructure isn't defined in Git and strictly version controlled, as far as the system is concerned, it simply does not exist. Being a senior engineer means recognizing that human and process bottlenecks are just as solvable and, frankly, just as critical as your application bugs.
Moving into Section 2, the illusion of scaling. Why more resources don't equal more performance.
Okay, let's look at a real-world production nightmare that I've personally seen bankrupt entire engineering budgets. Imagine your CEO wants faster feature delivery. Makes sense. So, you set up ephemeral staging environments for every pull request. Sounds amazing for developer productivity, right? But suddenly, developers are opening 50 PRs a day. Your CI/CD pipeline is now replicating your entire database and application 50 times over. Boom! Your AWS bill just tripled overnight, you've created a massive financial hemorrhage, and now finance is furiously knocking on your door.
So how do we stop the bleeding? A junior engineer will usually just throw more cloud credits at the problem, blindly cranking up Kubernetes memory limits or scaling up the minimum node count. But a senior engineer, they don't just treat the symptom, they systemize the prevention. They implement strict ephemeral boundaries, using tools like Kata to scale those PR environments down to absolute zero outside of business hours. They enforce 48-hour time to live, or TTL controllers, to automatically assassinate idle environments. And to prevent resource waste, they perfectly align memory boundaries so that requests exactly equal limits, which provides a guaranteed quality of service.
But hold on. Actually aligning those boundaries introduces a brand new architectural trade-off, the bin packing paradox. Yes, guaranteeing pod resources buys you rock-solid application stability, but you sacrifice density. You end up stranding unused memory across your cloud nodes, which means you are literally paying for thin air.
Let's put that into perspective. If you guarantee an app 2 gigabytes of memory, but it only uses 500 megabytes on average, you now have 1.5 gigabytes of stranded, wasted memory per pod. At a scale of 10,000 pods, that 1.5 gigabytes equates to millions of dollars paid to AWS for absolutely nothing. Efficiency at scale isn't about having a ton of resources, it's about how tightly you can pack them. You have to use tools like Carpenter and custom scheduler profiles to squeeze every single cent out of your compute.
Let's move to Section 3, the physics of the network, fixing the infrastructure path first.
Here is a puzzle for you. Why are 10% of your users suddenly getting 504 gateway timeouts when your dashboard says your average service CPU is chilling at a healthy 15%? I've seen entire war rooms spun up over this. Everyone is staring at that 15% average metric, completely baffled. Well, you've likely hit the hot pod paradox. Your load balancer is dumping 90% of your traffic onto a single container, while the others sit completely idle. This proves one thing for sure. Average CPU is a highly deceptive metric when you're diagnosing distributed systems. In fact, if you only take one thing away from this section, let it be this. CPU is a lagging indicator. Relying on it for scaling is a total trap. By the time your CPU actually spikes, user latency is already terrible and the damage is done. The absolute best metric for preemptive autoscaling in modern web services is concurrent in-flight requests. If your app starts to drag at 50 concurrent requests, you must configure your autoscaler mathematically on that exact threshold, way before the CPU bottleneck even forms.
And while we're under the hood fixing the network, take a hard look at your protocols. Ditching verbose REST APIs over HTTPS 1.1 with those heavy JSON payloads and moving to gRPC over HTTPS 2 using compact protocol buffers, that is a massive optimization. When you're processing millions of requests, the overhead of parsing all that JSON and doing constant TCP handshakes adds up to thousands of hours of wasted compute. gRPC multiplexes multiple requests over a single connection, bypassing those handshakes entirely. It slashes your network tax and gives you massive latency wins without changing a single line of your core business logic.
Section 4. Data, caches, and consistency. Protecting the company's most valuable asset.
We've secured the perimeter, but now we need to look at the heart of the system. Managing stateless apps is easy, but managing state and persistent data, that's where things get real. So how does a beautiful, lightning-fast, 100-millisecond page load locally instantly transform into a 10-second nightmare the second it hits production? You push your code, and suddenly the database is brought to its knees, quietly dying under the weight of thousands of redundant queries.
You, my friend, have just encountered the dreaded N+1 query problem. This is when you execute an initial query to grab a list of records, but then your code runs a completely separate query for every single individual record's-related data. If you fail to optimize this with eager loading or proper database indexing, a simple fetch turns into a total disaster that wrecks performance and aggressively inflates your cloud bills. The difference between 100 queries and 2 queries is literally the difference between an application that scales and one that collapses under its own weight.
So naturally, to protect your database, you add caching. But which pattern? You've got to weigh the trade-offs. Cache aside is a solid default, but you risk serving stale data. Write-through is great for strict consistency, but it hits you with high write latency. And write behind gives you incredible extreme performance, but carries a very real risk of data loss if a node crashes. A senior engineer doesn't just guess, they know exactly when to apply each of these patterns based on the strict business requirements of the data.
Section 5. The observability cost trap. The hidden price of seeing everything.
Okay, so you've optimized the app and you're monitoring everything to keep it stable. But watch out. Telemetry is fantastic until you realize your monitoring tools are secretly draining your company's bank account. Get this, many companies are absolutely horrified to discover they are spending 25 to 35% of their total cloud budget purely on observability tooling and telemetry storage. As your microservices scale, the volume of logs, metrics, and traces grows exponentially, quietly devouring your profit margins. And the absolute biggest culprit here? Cardinality explosion. This happens when metric data explodes because you're tagging metrics with highly unique labels. Let me give you a non-negotiable rule right now. Never use high cardinality values, like a user ID or a session ID, as a metric label. A Prometheus label with 10 million unique users creates a querying nightmare that can literally cost more than the application's actual compute infrastructure.
Fixing this requires serious discipline. First, implement tail-based sampling, meaning you keep 100% of your error traces but maybe only 1% of your successful ones. Next, use tiered retention, so you aren't paying premium storage prices for data that's months old. Third, shift those high cardinality IDs completely out of your metrics and into your logs. And finally, make sure your log handling uses asynchronous background buffers. That way, if your logging system blips, it doesn't block your main application I/O and cause a massive spike in user latency. Finally, Section 6. Delete code, save money, the ultimate architectural optimization.
We've covered the network, the database, the infrastructure, and your observability stack. But I'll tell you right now, the absolute most powerful optimization tool you have in your entire arsenal is your backspace key. You've got to keep the 10x rule in your head. Every single line of code you write will be read 10 times, modified 3 times, and debugged twice. Every line is a financial liability and a concrete commitment to future maintenance. The most productive thing you can do isn't writing more code, it's writing less code that accomplishes more. A seasoned engineer treats new code like a necessary evil, not a badge of honor.
I really want to leave you with this final thought for your day-to-day work. Next time you're handed a ticket to build a new feature, I want you to ask yourself, what can I delete instead? Look around for redundant logic, unused features, and those premature optimizations. Remember, the best code is the code that doesn't exist. So get out there, hunt down that technical debt, start hitting delete, and watch your system speed up while your cloud bills plummet. Thanks for hanging out with me on this explainer, and I'll catch you in the next one.